Hi everyone, in class this week we took a solenoid and we attached it to a ammeter. This particular one is a micro ammeter, and we got ourselves a magnet and we placed it in and out of the solenoid, and we saw that there was a voltage induced across the solenoid, and because of that voltage we saw a current flowing through the wires. We want to talk a bit more about this idea of an induced voltage across a conductor today. And the model we're looking at today is a straight wire, a straight conductor, as it passes across a magnetic field. The red crosses indicate a magnetic field into the page. The long line here indicates a wire as it moves across the page. It's moving with a velocity v. If we were to set this situation up and to actually measure this wire, we would find that there is a voltage induced across the wire. That voltage induced across the wire will end up having a positive at this end and a negative at this end for its polarity. The voltage will be related to how fast the wire is moving, how strong the field is, and how much of the wire is actually bathed inside of the magnetic field. We can tell that the top of the wire will be positive and the bottom of the wire will be negative using our right hand palm rule. Our fingers, as always, indicate the direction of the magnetic field. That's into the page. Our thumb indicates the direction of positive charge. So what is the positive charge? This is a conductor. It's full of positive and negative charges. As it moves across to that side of the page, the positive charges move to that side of the page. So our thumb is moving to that side of the page. Fingers into the page because that's where the field is, and so our palm is pointing up, which indicates that the positive charges will be pointed up. And if we were using our left hand for the negative charges, they would be pushed down, which indicates that our polarity for the voltage would be positive at the top and negative at the bottom. Velocity matters, field strength matters, length matters. So that gives us an equation. Voltage is equal to VBL. So the voltage experienced by this wire is equal to the velocity of the wire multiplied by the strength of the magnetic field multiplied by the length of the wire actually in the field. This equation can lead us towards a really useful and powerful equation called Faraday's law. To get from here to Faraday's law, we recognize that this wire is moving a particular distance across that magnetic field in a particular time. Distance over time, that is velocity. Rearranging that statement, we end up with, we do this deliberately because S multiplied by L is S multiplied by L, which gives us the area of the magnetic field that the wire is moving across. Area. Now this is starting to look like Faraday's law. We've got capital B for the magnetic field strength in Tesla. We've got the area of the actual field in meters squared, and the T is the time it took for the wire to move across. Now this is a dynamic process. Nothing is stationary, it's all moving. So it's not just B multiplied by area, it's the change experienced by the wire. So we're going to put in a capital delta here to remind us that this is not just BA, it's the change in BA experienced by the wire over the period of time that it took, the change in time. And this gives us Faraday's law. If you allow for the fact that BA is now going to be defined as something new, flux. See, up until this point, we've been quantifying magnetic field using Tesla. Magnetic field strength in Tesla represents the strength of the field at a particular point in space. Flux is another way to quantify magnetic field. Flux describes the total amount of field moving through a given surface area. Flux is defined as B multiplied by A. B multiplied by A. So now finally we can give the Faraday's law that we're all very familiar with. Delta phi over delta T, the change in flux over the change in time. Now this equation works for the wire moving across the field. It also works for the changing flux experienced by our coil when we move a magnet past the coil. There is no flux in the coil, there is flux in the coil, there is no flux in the coil. There is a change in the flux through the coil, and that takes time. So next week, as we pursue this idea of Faraday's law being equal to delta phi on delta T, the changing flux across a conductor, the changing flux across a coil, we're going to be able to use this to determine the voltage output from generators. That's the next step in this process. Okay, I hope that was useful.